All right, let's get going on the new stuff. So we started on probability the other day. Okay? Remember with probability, we had some ideas about, and we also did odds too, remember? But we said that probability with, how should I put it? Where is it in my notes here? Probability with mutually exclusive or mutually, where is it here? I'm losing it. Hang on. Here we go. Conditional probability and mutual exclusivity. If two items are mutually exclusive from each other, it means that they can't affect each other. So back to the example from yesterday. If we were picking cards out of a deck, and we wanted to pick a 2, and we wanted to see the probability of picking a 2 or a queen. Can those two things happen in the same pick? Can you pick a 2 and a queen in the same pick? No. Okay? So the probability of picking a 2 and a queen, probability of picking a 2 and the probability of picking a queen, okay, or the probability of picking a queen, we added those two probabilities. Okay? So the probability of picking a 2, all right, is how many 2s are there in the deck? 4, and how many total? 52, plus how many queens are there in the deck? Also 4 out of 52. So the answer is 8 out of 52. And you can reduce that if you want. Okay? That's how you get conditional probability for mutually exclusive events. Events that aren't mutually exclusive, such as the probability of picking a 2 or the probability of picking a diamond, are there 2s that are also diamonds? Yes. There are. Okay, so what you have to do is you can't just add them like this, because if you try to add them like this, you'll overcount all the different probabilities. Okay, so the probability, but you can do it this way. You add them and then you subtract out the extras. Probability of picking a 2, we already said, was 4 out of 52. What's the probability of picking a diamond? How many diamonds are there total? 13 out of 52 cards, minus the probability of being a diamond and a 2. How many 2 of diamonds are there? Just 1, minus 1 out of 52 gives you 4 plus 13, 17 minus 1 is 16 out of 52. Okay? Remember how to do that now? OK. Now we're going to talk about things slightly different. Now we're going to talk about, this is now section 11.7. Okay? And section 11.7 is events involving and conditional probability. Now conditional probability is different than mutual exclusivity. I'll show you. Okay, events including and, oops, and like that. All right. And we've also got conditional probability. And we'll get into what that means in a minute. Conditional probability. OK. Let's say we have 2 different events. In other words, we're going to pick cards. We're going to pick 2 cards out of a deck, or we're going to roll a die 2 times. We say that two events are independent events if the occurrence of either has no effect on the probability of the other one. If the occurrence, R-E-N-C-E, 2 R's, of either has no effect on the probability of the other. All right. if you have that, if you have A and B being independent, if A and B are independent, here's how you find the probability. Okay? The probability of A and B is just the probability of A times the probability of B. Okay? Here's an example. Draw a card from the deck, 52-card deck. Return it to the deck. Okay? And then draw another card. So you take a card, you go, phoom, there's my card, and then you put it back in, and then you take the second card. Do those two events relate, like, do they have an effect on each other? Is there any effect if I take one out and then put it back to the next time I do it? It's just like I started from the second one first, right? So it doesn't really matter. It's totally different than if you take a card out, put it aside, and then take another one. Those are actually dependent on each other. But if we pick a card and then return it, and then pick another one, let's find the probability of drawing a heart twice. Probability of drawing a heart twice. Well, it's the probability of drawing a heart times the probability of drawing a heart. So what's the probability of drawing a heart? How many hearts are there? 13. 13 out of 52. And we can just multiply it by the same thing again. 13 out of 52, because you're not, you aren't changing, or you're replacing the event. So 13 out of 52 happens to be 1/4, and 13 out of 52 is 1/4. So the answer here is 1/16, picking two hearts in a row. Okay. Sometimes gamblers get this wrong. Did you ever go to a casino? Oh yeah, most of you guys haven't been to casinos, you said. If you go to a casino and you play the roulette wheel, that's the one with the little ball that goes around and then it lands on a number. And also, and some of that, half the numbers are red, and well, almost half the numbers are red, almost half the numbers are black, and then there's one green one. Sometimes there's two green ones. That green one is where the casino wins all its money, by the way, because you can play red and black all night, and you get your money back. You double your money if it lands on black, but you lose it all if you don't land on black, right? It's almost 50% odds, or 50-50 odds, 1-to-1 odds, as we talked about the other day. Problem is, every time it lands on a green, people who put money on black lose, and the people who put money on red lose. And so that one time out of 36 or whatever they have is where the casino makes all its money. But point is that oh, sorry, that's not the point. Another point is gamblers sometimes think, let's say a roulette wheel hits red 5 times in a row. What's it going to hit the next time? Some people say black. Some people say, no, it's hitting red. It means it's going to keep hitting red. Unless the roulette machine's broken, each incident is completely independent of all the other ones. It doesn't matter what happened in the back, even though they write down the numbers. They have a little chart, and it writes down all the numbers so you can look at it. It's just so that people get fooled. But you know, casinos are in it for the money. OK. What's that?
There was a family that wrote down every number.
Yeah.
And found that it was kind of, the table wasn't as level.
Oh, well, there you go. They found the table. There's a family that wrote down the numbers and found the table wasn't level, and then what?
And they started playing the numbers that was most likely to hit.
And they started playing the numbers that were most likely to hit, and did they win billions?
They won millions.
Yeah, they won millions. Well,
They got
trust me, if you go to Las Vegas, the casinos there, every day they calibrate these things. Like they calibrate the roulette wheels. They make sure they're perfectly level, and it's just so that people don't do that. And the government comes in and says, make sure they're level and all that too, so you can't cheat. OK, another example with independent events. All right, is anybody in a family where you have 3 of the same, your siblings are all the same sex as you? All the same gender as you? No? Anybody you are? What do you have? 2 other brothers, obviously? 2 brothers? OK. What are the odds that there are 3 brothers in a row in a family out of only 3? Well, are they independent? Now, maybe. I mean, all right, some people say there's, some people have a bit greater ability to produce male children. Or, if you go through like the X-ray machine every day here, like you'll have no girl children or whatever. But no, let's pretend that it's mostly even, right? Well, what's the odds that the first child's a boy? 1 out of 2. Is that independent from the second boy? Sure it is. 1 out of 2 times 1 out of 2 independent from the third? 1 out of 2 equals 1 out of 8. So out of 8 families that have 3 kids, about one of them, roughly, will have all 3 boys. Or all 3 girls, I should say. Because that's the same odds for both those. My mom has 6 sisters. So what would 7 girls in a row? Would be 1 out of 2. This would be 7 times. So it's really 2 to the 7th, 1 out of 128, I think. Yeah. Wait. 2 to the 5th is 32. 2 to the 6th is 64. Yeah, there you go. So it's pretty crazy. They tried. My grandparents tried for boys, I guess, but no luck. All right. Now, remember how the other day we talked about the probabilities where the probability of something not happening is just 1 minus the probability of happening, and the probability of something happening is 1 minus the probability of not happening. We've got a similar case here. The probability of an event happening at least once, probability of an event happening at least once, okay, is equal to, you guys all right? Oh, it's just too warm in here, I know. That one, we'll see if that one works. Probability of an event happening at least once is equal to 1 minus the probability that the event does not happen. We'll see how long we can handle the loud noise from that one. I guess they never really fixed it, even though they did come that one time. So the probability of an event happening at least once is equal to 1 minus the probability that it doesn't happen at all. Here's an example. Anybody from Florida? Ever live in Florida? Yeah? Where do you live in Florida? Did you ever get hit by a hurricane? You did, yeah. So the probability that a hurricane hits South Florida, is it South Florida? Central. Probability that a hurricane hits South Florida in any year is 5 out of 19. So we'll say probability of hurricane equals 5 out of 19. OK? Question. What's the probability that it gets hit 4 years in a row? What's the probability it gets hit 4 years in a row? Let's assume that it's independent, because every year things kind of reset to it being independent. Well, we're going to do 5/19 times 5/19 times 5/19 times 5/19. Okay, when you multiply all that out, you can do it on your calculator if you want. That equals 625 divided by 130,321, which is about 0.0048, which is pretty small. About 1, what is that? 5 into 20 is 1/4. So about a quarter of the time, every year, you're going to get hit. But to get hit 4 years in a row, really small chance of that. Okay? Well, what are the chances, or what's the probability that you don't get hit in the next 4 years? Probability that you don't get hit in the next 4 years? All right. You do the same sort of thing. You say, well, what's the probability? Remember, what's the probability of getting hit in? This is the probability of getting hit. What's the probability of not getting hit? 1 minus that, which is 14/19. 14/19 times 14/19 times 14/19 times 14/19. If you do that on your calculator, that's 38,416 divided by 130,321, which is about 0.295. Yeah. The probability of getting hit is 5/19. The probability of not getting hit in one given year, not getting hit, is 1 minus 5/19, which is 19/19 minus 5/19. 14/19. Make sense? OK. Now, that's the way we would do each one of these. Probability of not getting hit in the next 4 years, probability of getting hit 4 years in a row. What's the probability of getting hit at least once in 4 years? So I'll put it up here. C, the probability of getting hit once in 4 years. Probability of getting hit once in 4 years. Do we know what the probability of getting hit every year? This, 0.295. Because that's what we said. The probability of not getting, well, probability of not getting hit in 4 years is 0.295. Therefore, the probability to get hit once is 1 minus that. So this is going to be 1 minus the probability of getting hit 4 years in a row, which is 1 minus 0.295, which is 0.7052, which is 70% chance. Right. So the probability of not getting hit in the next 4 years is 0.295. In other words, you're not very likely to not get hit in the next 4 years. Therefore, you are very likely to get hit at least once in 4 years. This is getting hit. What?
Isn't that the 1 minus p not hit in the next 4 years instead of getting hit in 4 years?
Oh, yes, thank you. Getting not hit in 4 years in a row. Getting not hit in the, yeah, not, how about just not? I'll just change that to not. Yeah, thank you. Probability of not getting hit in 4 years in a row. So this can be a little confusing. The probability of not getting hit in the next 4 years means you're not going to get hit in any of those years, right? The exact opposite statement is getting hit once in those 4 years. It's not saying what's probably getting hit every time in the next 4 years, because that's this, and that's actually much less, right? So really what we're trying to show here is this calculation is only for once, for an event happening once. If you want to figure it out for an event happening more than once, you got to do the longer math. But if you've already figured out the probability of not getting hit in the next 4 years, well then getting hit once in the next 4 years is just the opposite of that, 1 minus that. Make sense? All right.
So what is your formula for B?
What's the formula for B? Well, not hit in the next 4 years. Well, we know that getting hit in the next year is 5/19. So not getting hit next year is 14/19.
So is there such a formula, or you just?
You did it. We did it already here. You asked me this earlier, right? So what I'm saying is, to get look, the probability of getting hit next year is 5/19. What's the probability of not getting hit next year? 1 minus that. The probability of getting hit 4 years in a row is this time is 4 times multiplied together 4 times. Probability of not getting hit is 1 minus this multiplied together 4 times. The probability of getting hit at least once is 1 minus this one, 1 minus this one, which is 0.7052. So if Jeremy went back to live in Florida again, it's pretty likely that there'll be another hurricane coming through in the next 4 years. This is why his insurance rates are so high, right? Because they know that the odds are pretty good, or the probability is pretty good that he's going to get hit again with a hurricane if he lives there for 4 or 5 years. Make sense? I know it's a little bit tricky, but we gotta like process this in our brains. Questions on that? It's pretty well written in the book too, so. This is chapter 11. This is section 11.7.
Page 650.
Page 650, thank you. All right. OK, so those are independent events. Now we have dependent events. OK? Dependent events. Dependent events are when the occurrence of one does affect the probability of the other. One affects the probability of the other. Guys, that's killing me here. I know it's warm, but I don't know what's wrong with the other two. All right, we'll aim some that way if we can. Other side, push the other side.
Is that all?
That's good. No, push, there you go. I think it's as high as it goes on that one. Yeah. All right, dependent events. One can affect the other. All right. If A and B are dependent, A and B, it's a terrible B. If A and B are dependent events, then the probability of A and B occurring, okay, equals the probability of A times the probability of B given that A occurred. Okay. By the way, some of these are on your formula sheet. I don't have an example here, but some of these are on your formula sheet. Thank you. All right. So if you look, well, we've got P or and P probability of A or B, and that's not what we're talking about right now. We've got probability of B given A. Yeah, probability of B given A. Okay, which, well, it's actually not written right there. This one's not on your formula sheet. I guess I lied. But I'll show you an example. Okay, here's an example. Draw a card, but don't replace it. Okay, and then draw another card. Now we've got the first event affecting the second event, because that card is gone. Okay? Here's how you do. So event A. Let's say event A is first card is a heart. First card is a heart. Event B, second card is a heart. Second card is a heart. All right. Well, the probability of A and B, probability of A and B, in other words, you're picking both, equals the probability of A times the probability of B given that A occurred. All right. This is not too difficult. First card is a heart. How many hearts are there? 13. Out of how many cards? 52. That's times. Now, if we took a heart out, okay, now we know that that's affected. So now we need to figure out the probability of a heart given that there's one missing. How many hearts are left? How many cards are left? 51. There's your answer. 13 times 12 divided by 51 times 52, or 156 divided by 2652, or 1 out of 17. Okay, that stuff's not too hard. Not too bad, I hope. Okay. All right. Now we get into conditional probability. Okay? Conditional probability means that, well, that basically means the same sort of thing. The probability that event B, given that event A, happened. Okay? We rewrite this conditional probability as probability of B and we draw a line like this, a vertical line, A. It doesn't have to be that big. But probability of B given that A occurred is how we write this. Okay? What you're doing is you're saying that in this case, we actually are looking for just this, probability of B given A. It's kind of taking out this part. Okay? But what you have to do is you have to think of this part anyway, because you need to figure out what the answers are here. So what's the probability of getting a heart if I've already taken one of the hearts out? Well, it's 12 out of 51, because there's 12 hearts left and there's only 51 cards left. Good? Okay. All right, let's do a different example. Probability of B given A. And this one is in on your formula sheet. Okay? All right. OK, you select a letter from the alphabet. Okay? A, there you go. If you select a random letter from the alphabet, find the probability of selecting a consonant. Probability of selecting a consonant. Then I'm going to put a little if in there in a minute. But what's the probability of selecting a consonant? How would you figure that out? How many total numbers of letters are there? 26. Hey, what's the last letter of the alphabet? I'm only tricking you. I'm saying this. All right. I shouldn't trick you. The last letter of the alphabet is Z, right? Not if you're Canadian. What is it? It's Z, which is how they pronounce the letter Z. You guys know that? If you go up to Canada and they sing the alphabet song, it's X, Y, Z. I swear to you. England's the same way. England's the same way, yeah. Yeah, Z. Anyway, 26 letters. You would have to count up all the consonants. Okay, how many? Let's pretend Y is a consonant. How many vowels are there? 5. So there's going to be 21 consonants out of 26. That's going to be the probability of just picking a consonant, right? But let's say we're saying let's select a consonant given that the letter selected is before J. Now what do we do? Selecting a consonant. You got to just figure the letters between A and I. A, B, C, D, E, F, G, H, I. There's how many? 6. 6 consonants. And how many total letters are there between A and I? A, B, C, D, E, F, G, H, I. 9. So the probability of selecting a consonant, and then I'll write it properly, given that the letters precede J. Okay? Selecting a consonant given the letters precede J, 1/3. 1/3. I've been playing my mom on Scrabble on my iPhone. She has an iPhone, and I have an iPhone. We're playing Scrabble. She's crushing me. It is 2/3. She would crush me in math, it looks like, too. OK, so all right. So yeah, 2/3. Selecting a consonant out of the first 9 letters. OK? All right. That is conditional probability. All right. Example. Another example for you. A card is drawn from a 52-card deck. What is the probability that the card is the 2 of hearts if it is a heart? How would I write that, first of all? Probability that the card is the 2 of hearts given that the card is a heart. What's the total number of 2 of hearts in the deck? If we're only checking the hearts, what's the total number of hearts? There's your answer. See, this isn't so hard. This stuff isn't too bad. Okay, 1 out of 13. All right? OK. Let's take our break early, because it is hot in here. Maybe we can fix the air conditioner. But when we come back, we're going to work on, we're going to shift gears. That was all probability and combinations and permutations. The next thing we're going to do is frequency distributions. So like bell curves and things. We'll get into that. All right, come back right on the hour. 6 p.m., please. There's too much noise pollution at this place. Getting a headache. All right. OK, so we finished chapter 11. Chapters fly by in this class, if you haven't figured that out yet. We are now on to chapter 12. In fact, section 12.1, which is on what we call sampling frequency distributions and more graphs, but not graphs like the kinds we've been doing before. Graphs of distributions of data. Okay? So we got a lot of times when we start these chapters, we have to get a little bit of vocabulary out of the way. Okay? First part of the vocabulary is a population. Population consists of people or objects. We can have an object, a certain set of objects, which we call the population. Objects whose properties are described by a data collection. This is the kind of thing you get when you look at polling data, something like that. So if you're taking polling data for a certain group, you've got the population, which is everybody that could be chosen for that polling data. Okay? A sample is a subset of the population, is a subset of a population. Sample is a subset of a population. So if you are taking a certain number of people from that population, that might be a subset. Now, subsets, or samples rather, that's a sample. Samples rather should be, if you're looking for a reasonable distribution, should be random. Sometimes they're not. If I picked, out of the people in this room, I just picked people in the front row, right? Well, that's not a random sample, because maybe there's some reason the people in the front row want to sit in the front row all the time. OK? So that's not a random sample. But we have an idea of a random sample. A random sample, OK? It's a sample that's obtained, is a sample, okay, such that every element has an equal chance of being selected. For the sample. An equal chance of being selected. How would I randomly choose a sample of 5 people from this class? What's one way to do it?
1, 2, 3, 4, 5.
Yeah, but how do I pick those people? Race? Probably not, because that's still not random. Because you wouldn't necessarily, like, there's certain people of one race and the other, right? And that's not a random sample necessarily. But the best way to do it might be for all you guys to write down your names, put them in a hat, juggle that all around, and then me pick 5 names out, or somebody pick 5 names out. Wouldn't that be a random sample? That would be a completely random sample. Now, if you wanted a sample that had a certain percentage of all the races in there, that's a different story. That might be a different type of sample. But each individual sample, you might want to pick a random sample from each race, let's say. But in terms of the general total population, random sample is Everybody has a completely equal chance of being selected.
So the lotto,
The what?
the lotto, the game.
The lotto. Yeah, the lotto is.
Like
So
random number.
yeah, you know how they choose the lotto? They have little ping pong balls, and they all have numbers on them, and then they spin them around in that giant machine. And then every so often, they push a button, and then one goes boop and pops out. That's random, a random sample. Like those 5 numbers are supposed to be a random sample of all of them. Okay. So the method is the important part for choosing this sample. The method itself is important. Because I can't just pick the 5 of you, the first 5 that come in the door. That's another way. You could say, oh, the first 5 people who come in the door out of everybody. Well, people who come here early tend to be may have different properties than the people who come later. Something like that, right? So that's not a random sample. The best random sample is to have everybody and then just grab, like have an unbiased way of grabbing them. Okay. All right. OK, so we've got this idea of population samples and random samples. Once we have that sample, we need to somehow summarize it. Okay? For whatever quality we're looking for. Okay? So I pick 5 people in this room, and I want to know the height of each person, or the height sample of the sample of people, right? Well, I then take the height of each of those data points, okay, or data items, and we put them into this chart that we're going to create. Okay, so we're going to come up with what we call a frequency distribution. Okay, a frequency distribution for the data items. Okay, each element, I'll get to what a frequency distribution is in a minute. Each element in the sample, is a data item. Okay, so if I say, well, this data item has this property, well, that's because I picked that one item. Okay? All right. Let's say we picked 10 people in here, and we measured their heights, like we said. Okay? 10 people, and we measured their heights. And their heights, our data set, if you want, our data set is as follows. 68, 73, 69, 70, 73, 70, 67, let's see, 70, 66, and 72. I get 10, 1, 2, 3, 5, 6, 7, 8, 9, 10. Okay? I can do a frequency distribution by doing the following. If I have 2 columns, like this, column 1 and column 2, okay? The data values, okay? The people, we'll say, people heights. Okay? If I write down all the different numbers that show up, let's say in order, 66, 67, 68, actually so even ones that don't show up. Let's say I write down all the ones from 66 all the way to 73. 69, 70, 70, did I get them all? 67, 69, 70, 71, 72, 73. Okay? How many 66s are there? 1. How many 67s? None. How many 68s? There's a 67. There it is. 167. How many 68s?
1.
Also 1. How many 69s? 1. How many 70s? 3 70s. How many 71s? 0, 71, 72s. 1 and 73s? 2. Okay? That is our frequency distribution. It shows the frequency, how frequently each one of those occur. Okay? And we'll get to how what other things we can say about this in a little bit. Sometimes frequency distributions get a little hard to read if there's so many different numbers. Okay? So in our sample here, well, this isn't too bad, right? But if there were lots and lots and lots, if I just kept writing, you know, if I did babies all the way up to like tallest people in the world, this could be like, well, like, you know, 10 inches or 7 inches or whatever babies are, all the way up to, I don't know, how the tallest person, right? 80-something inches, right? And it'd be really hard to read in this form. Okay? What we can do is we can group them into classes. So for instance, I could just write, this would be kind of a silly way to do it, but I could write this. From 5 feet to 5 feet, 5 feet 11 inches, and 6 feet to 6 feet 11 inches. That could be a much easier chart in this case. What's the cutoff for, what is 6 feet? 6 times 12 is 72. So this one's going to be 72 greater than or equal to 72, and this is going to be less than 72. OK, so let's see. Going up 72. 1, 2, 3, 4, 5, 6, 7. That's it. 7, and the rest 3. So if you can group them into groups, you should be able to do that. The total, n, equals 10 still. OK? And we had 10 over here. N equal to 10, number of people. When you do a class like this, do you want to do, like, I don't know, 5 feet to 5 feet 1, and then 5 feet 2 to 5 feet 10, and then, no, you want to have the samples, you want to have the groups the same size if you can. Okay, it makes it easier to do that. This is called the width of the group. Okay, how wide it is from 5 to 5 feet 11 inches. Okay. All right. By the way, on page 679, you definitely want to look at that in your book. On page 679, you've got examples of the next things we're going to talk about here. Okay. The next things we're talking about are what we call histograms. Uh-oh, I hope I don't need this data. I might. Nope, I don't. Histograms are a way to visually see on a graph these frequency breakouts. Okay? A histogram is just a bar graph where the bars actually touch. Okay? So I could have, let's see, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And 65 could be right there. And 77 could be right there. In this case, you can, let's say we looked at these, and this was the range between, I don't know, 60. Well, this is not a great example. It's not 7 in this group. But this would be what it would be like. In this case, this bar reads 7, because it's right across here from 7. And this bar reads, let's say, 3. 3 from there. Okay? This might be a histogram of the heights of these people. I guess the one I had up here before where it was, this one's going to be 5 to 6 feet. So this is going to be 5 to 5 feet 11 inches, and this one's 6 to 6 feet 11 inches. I think there are 7 and 3, which is I think what it was before. Okay? This is called a histogram. Okay, and we need to know how to do those. What's that? Okay. We can also turn a histogram into what we call a frequency polygon. Okay? A frequency polygon is actually pretty easy to do. Okay? You put a dot at the top of each rectangle. Okay? And then you just go down to the beginning of each range, and you do the line dots between them. Okay? That's a frequency polygon. Or yeah, a frequency polygon. Okay? So yeah, what you're going to do is it's going to end up looking like this. You're going to get rid of the bars, And you're just going to go the top of that one to the top of this one, and then down here, connect the dots like that, and down like that. And that's what this is a frequency polygon. A frequency polygon. Polygon. I don't know what I'm doing here. Poly, P-O-L-Y-G-O-N. A frequency polygon. All right. We can also do this thing called a stem and leaf plot. I've never actually in my life seen a stem and leaf plot in the wild, but we talk about it in math class just to show you guys what it is. Anybody still drawing the histograms? OK. Or the frequency polygons? We can do this thing called a stem and leaf plot. What a stem and leaf plot is, it basically draws out your histogram in numbers. So what we would do, let's see what we would do for this one. Here's what we do for these. Okay? We would say, let's say 4, 5, 6, 7. There's actually no 4s and 5s, but we can do this. What you do for each one of these is each time you go to each number, and the second digit, you just write it up here. So for this one, it would be 68. And then this one, 73. And then this one is a 9, so you'd write a 9 there. And this one is a 0, and this one's a 3 for the 7, and this one's a 0, and this one's a 7 here, and this one's another 0, and this one's a 6, and this one's a 2. Okay? So you see how this is it's kind of like the histogram if you were going from 60 to 70 inches and 70 to 80 inches. If you turned it sideways, this bar would be this tall, and this bar would be this tall. Right? If you kind of flipped it sideways like that. Right? And it gives you somewhat of an idea of where in the range they hit. Like if you look at the 70 range, well, most of them are 70. You can go, OK, it's pretty low 70s. We're not talking any high 70s here. And this shows you high 70s. If you were to just do a histogram of this data, it would look like this. Let's see. 4 and 5, 6, 7. So well, 1, 2, 3, 4, 5, 6. Did I miss one? Oh, no, that's it. 6. This would be 6. There we go. So this one would be from 60 to 69, and this would be 70 to 79. And it would look like that. Can you tell where the range is in this one? Like of the 70s. It kind of looks like it's kind of maybe in the middle, but it's not really in the middle of the 70s. No 70s, none of the 70s are even above 73. So sometimes this is a little better way of representing it. I don't think I'm going to ask you to draw a stem and leaf plot. But you should know how to do it, or you should recognize it anyway, if it comes down to it. Okay? All right. Now, you guys have all done the following before. If I have a bunch of numbers, what are some of the things, what's one number I can tell you about these numbers that might give you some idea of what these numbers represent? In particular, if I were to give you all these numbers, and I were to say, give me one number that represents all of those, what would you do?
Average.
The average, right? Or what we call the mean. Okay? We call the mean, and there's two other things. Anybody remember from when you did them before? Mode, mean, and median. Not medium, median. Okay? Those are called measures of central tendency. Measures of central tendency. Okay, this is actually now already 12.2. I know, it sounds like a sickness. Measures of central tendency. Tendency. What this means is it's just telling you something about the data set and something about the middle part of the data set. Something about the data set so that you can say, I see how that data set taken as a whole is represented, okay? So it's kind of like a typical normal representative. So we're looking for what is a typical or a normal or a representative, E-N-T-A-T-I-V-E, sorry for the, a representative value for a data set. Okay. All right, we've got the mean. And I'm not talking about somebody who's like not very nice, right? The mean, we've got the median, and we've got the mode. We're going to go through how to do each one of these. Okay. All right. The mean, the first one, the mean, we designate the mean like this, x with a bar over it. Okay? You can actually call it x bar if you want. It's also called the average. It's also called the average. Okay? If we had a data set that looked like the following, 13, 13, 14, 14, 15, 16, 16, 17, 17, 17. Okay? There's 10 of them there. Count is 10. How do we find the mean? Add them all up. Divide by 10. Okay? So you add them all, and I'm not going to make you add them all, but you could. Not too hard. Add them all, you get 152. Okay? So x bar, or the mean or the average, is 152 divided by 10, or 15.2. That's the average. Is the mean one of the values? Not necessarily. Sometimes it turns out it is, but not always. Okay? In this case, it's not. The mean is not one of the values. Okay? There's definitely some different types of questions you can ask about this. Okay? Let's do a frequency distribution of values. And then we'll see if we can figure out the mean from it. Okay? Here is our chart for a frequency distribution. It's for grades on an exam. It's not your grades. X, frequency, and the, let's see, x times the frequency. There we go. Okay? 35, 37, 42, 58. You guys do much better in general in this. 60, 62, 74, 78, 82, 84, and 95. Okay? 1, 2, 1, 1, 5, 3, 4, 4, 2, 1, 1. That's how many people got a 35, 1. That's how many people got a 37, 2. That's how many people got a 42, etc., all the way down to here. Okay? There happen to be 25 students in this class. Okay? In order to get the mean of this, you would have to add 35 plus 37 plus 37 plus 42 plus 58 plus 60 plus 60 plus 60 plus 60 plus 60. Or you can just multiply these out. The score times the frequency. 35, 74, 42, 58, 300, 186, 296, 312, 164, 84, and 95. Add all those numbers up, and you get 1,646. there are 25 students in the class. Adding up all the different grades for everybody gives you 1646. How do we find the mean? Divide what by what? 1646 divided by 25. And you get a mean in this case of 65.84, which means they didn't do so hot on it, I guess. But you never know. I had a physics class in college where the average grade was on tests was something like 29 or something like that. If you got a 5% on the exam, you'd get a D in the class. That's how bad the grades were on these things. Okay? In general, okay, the mean is written the following way. X bar, or our first Greek letter, I think, sigma x times the frequency divided by n. Anybody remember what that sigma symbol means? It means sum. Okay? Sigma means sum. So you add up all of the individual values for the scores times their frequencies, which is what we did. Add all those guys up. And then you divide by the number of the total frequency, I guess. The number of all the total frequency. Okay? So in this case, I'm not going to make you, I'm not going to rewrite this. They're not going to make you write this. But you should know that that symbol means sum. So this is going to be x bar equals the sum. You add, 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 add. Okay? That's how that one's done. Some calculators actually have a little sum button. I don't think the ones I gave you do. Some of them do. Okay. All right. Here's another type of question we can ask about these frequencies with the mean. And this is one that gets very important the day before the final, because you might want to know if you're going to be able to do well, how you're going to do in the class using this method. Because I will tell you all the different various points up to that point. So let's say that there are, there's 6 exams in a classroom. On the first exam, you get a 50, and then you get a 72, and then you get a 41, then you get an 85, and then you get an 82. What score do you need? What score do you need for the last exam to get 70% average for the class? Do we know how to figure that out? Christine, how would we figure that out?
You write down all the numbers.
Okay, 50 plus 72 plus 41 plus 85 plus 82. Is that what you'd do? No?
Yeah.
Okay. You need a what? Well, I don't know. Let's find out. What? So, okay, so you write all these down, then what do you do?
I already forgot.
Oh, no. Somebody else. We're almost there. We've written all these down. Plus x. Yeah, plus some unknown value for a test that you haven't taken yet. And then you divide by what? 1, 2, 3, 4, 5, 6, because there's only 6 total. And that gives you what?
70.
Yeah, 70, because that's what you want to get. And it is 90, as it turns out. But what you can do is you can add all these guys up, first of all. That gives you 330 plus x divided by 6 equals 70. Do we know how to solve for x? We sure do. Multiply both sides by 6. 330 plus x equals 420. Subtract 330 from each side. Right? X equals 90. So you got to do pretty well on that last exam to get a 70 in this, on this set of exams. Yeah. Questions on that one? I can definitely see asking you that question, that type of question. What's wrong, Christine?
3 plus 6, plus x divided by 6.
Yeah. Why is it 6?
6 exams.
6 total exams. Good.
So how did you get 420?
Oh. Okay, so this is what it's 330. I added all 330 plus x divided by 6 equals 70. Then you got to multiply both sides by 6 to get rid of the 6. And you do that. Okay? All right. Okay, so that's the mean. Now let's talk about the median. Does anybody remember what the median is? From the middle. I like that answer. It's almost correct. I mean, it is correct, but there's one little piece you got to remember. The median. Yeah, you average the two in the middle if they are not the same. OK, so the median, what you do, one, arrange the values from smallest to largest. Smallest to largest. That's the first thing you do. The second thing is for an odd number of items, the median is the middle number. Okay. For an even number of items, okay, the median is the mean of the two middle items. Okay, it's the median of the two middle items. Okay. 12, 17, 8, 20, 10, 8, 10, 10, nope, sorry, 10, 12, 17, 20, and 12. What's the median of that? Well, we have to figure it out. I'll start writing them down if you guys start writing them down on yours. I'll cross them out when I get to them. 10, 10, 12, whoops, forgot an 8. 10, 10. Oh, there's two 8s. I'm not reading very well. 8, 8, 10, 10, 12, 12, 12, 17, 17, and 20, 20, and another 20. No, there's two 20s. Yeah, two 20s. OK. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. It's got to be that one. Right? And if I had added another 8, let's say, well, now you're going to go 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. It's going to be average of those two. It's still going to be 12, but you'd have to take the mean of those two. Right? Okay, good. Why do we care about the mean versus the median? Well, let's take a look at an example where it might make a difference. Let's say that you had some employees, and here were the salaries, average salaries. $19,700, $20,400, $21,500, $22,600, $23,000, and $95,000. All right? What is about the average salary, just by looking at it? Not the average, but like the typical salary? 20-something thousand, around 21 maybe, right? That's kind of the typical salary. If you figured out the mean, if you add these all up and then divide by 6, right, the mean is actually $33,700. That's the mean. Okay? That really doesn't tell you that much about it, right? That doesn't really say much because this guy outweighs a lot of people, right? I mean, it's like looking at the average salary at Microsoft is like $180 million a year, right? That's because the top 2 guys make over $1 billion a year, or something like that. I mean, it's not quite that much, but it's you know, Bill Gates and Steve Ballmer make like millions and millions and millions a year, and they outweigh all the people at the middle. You know, the typical salary at Microsoft might be $150,000 a year or something. It's actually pretty good, or maybe $100,000 or something. But whatever it is, the point is you don't want to take some of these outliers into effect. Well, let's figure out the median. 1, 2, 1, 2. You got to take the average of these two. 21,500 and 22,600. Add those up, divide by 2, and you end up with 22,050. Is that more like a typical salary? Yeah. So the good thing about the median is it's less sensitive to extreme values. Okay, so the extreme values, because they don't even come into play, they kind of get wiped away. The stuff that's right near the middle will generally give you a typical value. It's not always true. I mean, you know, it's not always, it doesn't always work out that way. I mean, you could have like 1, 1, 1, 1. Well, actually, it would work out in this case. I was going to say 1, 1, 1, 100, 1,000, 10,000, right? Well, what's the median here? 1, 2, 3, 1, 2, 3. It's 1, right? Well, a typical value, if you're saying 1 is a typical value out of all those, that's not necessarily helping you too much there. Okay, but you know, it's still useful for certain things. Okay, so that is the median. All right. Does the median have to be in the set of values? No, of course not. If you're taking an average, it's not. If you're taking the average of these two, a lot of times it is. If it's an odd number, it's definitely in the middle. It is a member, but sometimes it's not. The mode is what? Remember the mode? It's the one that comes up the most. Okay? The mode is the value the data value that occurs most often. The mode. The value that occurs most often. Okay? There actually can be more than one mode. There can be more than one mode. Okay? What's that? Yeah. Can be one mode. All right. 13, 13, 14, 14, 15, 16, 16, 17, 17, 17. What's the mode? Mode is 17. It happens 3 times, 17. Right? 2, 1, 4, 5, 3. What's the mode? No. It's either no mode or all of them, depending on how you want to discuss it. Either way, you can. Most people would say there's no mode there because they're all the same. But I would probably accept all of them are the mode. Okay. How about 2, 1, 3, 4, 6, 3, 5, 6? There's 2 3s, and there's also 2 6s. So it's bimodal. Means there's 2 modes in this case. 3 and 6 are the modes. Okay? Does the mode have to happen in the set? It has to, yeah. Unless you're saying there is no mode, and then it's not there. But if there is a mode, it has to be in the set of numbers. Okay? All right. here's what we're going to do. We are actually going to stop me screaming at you today. But we've got two things I want you to work on. I handed this out yesterday. Did everybody have this sheet? It says, let's see, it says 11.3, 0.4, 11.6, 11.7. This is not on the new stuff we just covered with it's just on the stuff that's probability related. Okay? I want you to work on that. And then I'm finally going to give you a bunch of word problems that I've been meaning to give you for a while. I know, you hate them, I know. I've been meaning to give you these for a while, and I'm finally going to give these to you, so I want you to work on those as well. Let's take a break now, come back at like 5 of, and then we'll get working on this stuff. Sound good? All right.